let's go ahead and take a look at this problem here. We have some things being diagonal. Let's be really clear. So we have quite a few coefficients of friction. We have mu between 1 and 2 here, which I'll call mu S1 static 1 and mu kinetic 1, depending on whether it's moving or not. And then here we have mu static 2 and mu kinetic 2, depending on what's going on. So we're going to say that M is small enough that the blocks remain at rest when released. So let's draw some forces. So we have here N1 and then M1G. And so what this tells us is that the normal force is actually equal to M1 times G, because that's the weight of 1 due to the Earth. Now here, this is an interesting thing, because since M is pulling M2 and this sits still, there's nothing trying to move M1, so it turns out F1 is actually 0. This is sitting still, so there's no push or pull on M1 at all. There's nothing trying to, like, it's not grabbing M1 at all from underneath. And then the tension exerted on block 2 by the string. So we've got tension. We're going to have the normal on 2 due to the table. We have the weight of 2 due to the Earth. We're going to have the mass of, we're going to have the normal on 2 because of 1. And let's see if we can actually figure out what this third law, what the force is going to be. So we know because of this rope, we have T here, and we have big mg here pulling down on M. So it actually turns out the tension in the string is going to be capital M times G. Now, the normal force exerted by the tabletop, I'm just going to actually copy all this free body diagram stuff here. You only needed to draw one of these forces, but on each of these blocks, we'll just go ahead and move it all here. So, let's figure this out. So we have normal on 2 due to the surface equals weight of 2 due to the Earth plus the normal of 2 due to 1. But we also have here that the normal on 1 due to 2 is mg, so we can actually employ Newton's third law to help us right here. Whoops. So taking all that into account, I'm going to get that the normal on 2 due to the surface is going to be m1 plus m2 times g. The friction force exerted on block 2 by the tabletop is going to be F is mu 2 static times this normal force that we got in 4, which is going to be m1 plus m2 times g. That's the idea for that normal force. And then to actually get the amount that the force on B for it to remain, or the force on B, so the blocks remain at rest, let's be clear here. So basically we need the tension force to be bigger than this friction force. Let's actually be careful. Let's do this with our free body diagram. So we also have, and I left out a force here, we actually have the friction on 2 due to the surface and the friction on 2 due to the surface here. I'm sorry I left those out. So what we need is we need tension minus friction equals 0, but we also know that the tension is equal to mg from the previous thing. So in other words, if our tension is just a little bit bigger than what we're going to solve for here, okay, so if tension is just a little bit bigger than this, we'll be able to get the things moving. So we're going to have mg minus F is greater than or equal to 0. So mg is greater than or equal to the friction force. I'm just substituting here. and then the friction force is this here. So we need M to be bigger than M1 plus M2 times G, or the blocks are not going to move. So I'll do part C and D in the next